AC and DC, electric motors. And then of course we have fluid power motors too. So I think in uh, in fluid power, I think I'll hook up a motor. But the problem we have over there is the piping is this. I don't know, like maybe good gracious, maybe 3-4 millimeters, and we're running the pump is all the way downstairs, or the compressor is all the way downstairs, and the piping's so small it's hard to runs those motors. So here we go. So most of our, of course, all our motors on our manufacturing line are DC. You'll run into both of them in industry though. DC used to be the predominant motor for speed and torque control. So what you'd do is you'd have a DC motor, but you'd take AC, you'd convert it to DC, do what we call a DC drive, and then you would do the DC drive to run the motor. And you could run it at any speed you want to, from no load to full load. Very reliable depending on what type of DC motor you have, and you can control it precisely. But the problem is their DC motors are a lot more expensive per horsepower. AC motors work off, most AC motors, we have a few out there that works off the principle of induction, which basically means, when we look at them, they're a lot cheaper per horsepower. So as soon as they figured out how to control those guys, we can't control them as good as we control DC. So it's kind of like hydraulics and pneumatics. If I want to control something precisely, then I'm going to use hydraulics. If I want to control something sorta, right? If I'm not really concerned with the speed of the actuators, how fast they've got to move, then I will probably use pneumatics. Well, that's the same thing with AC. AC motors, we can control the speed, we can't control the torque. AC motors wants to do the same torque all the time. DC motors, we can control not only the speed of the motor, we can control the torque of the motor. But now we take AC, we convert it to DC, we convert it back to AC to run AC motors. So the drive unit costs about the same. So what they're saving all the money on, they're saving them on AC motors. And so the predominant speed control method now is AC. So DC motors, the DC motors we'll look at is shunt motors, series motors, and compound motors. We'll look at stepping motors. I can't get my stepping motor to work, guys, so we'll have to. And we have brushless DC motors, which are really becoming popular, very, very expensive hand tools, like hand drills. You can get, but you ever priced a brushless drill yet? The only real advantage you get on those is better torque, but you can use those in gaseous environments. In AC, we got capacitive motors, we got single phase motors, capacitive start, capacitive run, split phase, and shaded pole. We have 3-phase motors, we have Y motors, delta motors, we have Y delta motors, and wound rotor motors, which you don't see much anymore. And then we have synchronous motors, which we see every once in a while. So a DC motor, the way a DC motor works, and I'll pass this around. By the way, what's happened on this one, I'm going to pull the cover off of it, is you can actually see the brushes that are tore up. So this is why DC motors are so expensive. No reason they'll eventually go bad. So what we have is we have the outside field is going to be stationary. But the way all motors work, and I don't know if I put that, but I need to put that, all electrical motors works on the attraction and repulsion of magnetic fields. And everybody understand that, right? So this probably won't show up on my video, but oops. So we have like poles do what? Repel. and then unlike like poles repel and unlike poles retract. So I have two magnets, and of course this would be like poles. And then if I come up here and turn it around, this is unlike poles. So this is the way we create motion with electricity. This is the way all electrical motors work. It works on the attraction and repulsion of a magnetic field. One of the fields has got to move. So what we do on a DC motor is we have a wound armature, which some people incorrectly call that a rotor. We use that term on AC motors. If your boss calls it a rotor, that's fine, but you need to understand. And then what we do is we transfer electrical energy into the armature with what we call a commutator. So what happens is we have magnets on one side, then we have this on the other. So this is always north, this is always south, this might be north and this south, and the dang thing's going to do what? It's going to turn. But as soon as it turns, we switch the rotor. So we're constantly opposing and attracting magnetic fields. So DC motors has to have a wound rotor around it's got to be wound. And of course it's copper and it costs a lot of money. Plus, when you look at that thing, these brushes are going to wear out. So a big DC motor, you will have access to those brushes. So you're going to have to replace them every once in a while, right? You understand? And also, when these things switches, there's going to get garbage on the commutator. So by the way, the thing that does the switching is called the commutator. And it's going to be slotted so you can actually see it on that DC motor. And the brushes, you can see what happened on that one is that thing was sealed and it was actually twisted to get in there, and we didn't, and the brushes just finally wore out on them. So the brushes are gone. By the way, on your alternator it's spinning a electromagnet, so you got brushes on that thing too, and eventually it will wear out. And sometimes you can replace them, sometimes you can't. I had a DC, a Dodge van was driving down the Gulf Shores, and the alternator went out on it. I popped the brushes out of the thing, which so it was real easy to get to, and and replace the brushes. You know how much the brushes cost me? $2. How much would the new alternator cost? A lot, yeah. So. But that's back when they was replaceable. Most of the time you can't even get into the alternators anymore. So we have a field. So the field can be, this is what we call permanent magnet motors. So permanent magnet motors, the field, so the outside we call it the field. This thing called it the stator, but technically we call it the field. And then we have the armature. The armature rotates within the field. Permanent magnet motors, we can't change the torque on them. But these are the cheapest. These are going to be the fractional horsepower motors. This is what runs except for the stepping motor, this is what's on all the motors on our lines over there. This is what's in your car. So every car but the starter in your car, your starter is not a permanent magnet motor. So the motor that runs your windshield wipers is a permanent magnet motor. Probably the one that runs now most of our cars have motors on the radiator, because most of our cars now are front wheel drive, right? And your radiator's off to the side. Older cars, the radiator was in the car was a rear wheel drive, so it was mounted forward, and the fan actually ran right off your motor. You didn't run it electrically. But what's nice about controlling is that you can turn it off or turn it on and make your car run more reliable. Commutator, a slotted copper ring used to transfer current from the source to the armature. The slots mechanically change the direction of current in the armature, causing the motor to rotate. Brushes, these are carbon blocks with copper wires attached, used to transfer the current from the power source to the commutator. Normally, we can reverse it two different ways. We can't do this one because that's a permanent magnet. but we can literally reverse it two different ways. We can reverse the connection on the field if we got electromagnetic field, or we can reverse the connection on the armature. If you reverse both of them, it'll run in the same direction. It won't, because you got to swap the relationship between the fields, right? That's also true enough. We normally change the polarity on the armature. That is the industry standard. I've never seen one change with the field, but I'm not going to say you're going to run into that because we run into problems with screwing around with the field on some of our motors. Okay, any questions? So this is a shunt motor. So here, shunt means in parallel. So it means the field's in parallel with the armature. This is the symbol of the armature, by the way. And they're usually split apart. On a split phase motor, we don't use. I'm sorry. On a permanent magnet motor, we don't have a symbol for the field because why? It's permanent, right? So a shunt motor, this is a separately excited motor where we can electronically control the field. So we increase the current to the field, the torque goes up. The speed goes down, torque goes up. So you don't get anything, you don't get more work out of it, right? You understand that? So I can control the torque with the field, and then I control the speed with the armature. So the more current you put through the armature, the faster motor is going to run. Because you create more current, the magnetic field goes up. So we can control the speed with controlling the armature current in the same direction. If you control the speed with the field, it's opposite. So if you increase the current to the field, the motor slows down, but torque goes up. So we had some motors out at US Steel, compound motors, and we literally control both of them. So if they wanted to increase the torque and leave the speed alone, they would increase the field and increase the voltage on the motor to cause it to run the same speed. It was really cool system. Good speed regulation over varying loads. Okay, starting torque. Separately excited, changing armature voltage current, changes the speed in the same direction. Changing the field current changes the speed in the opposite direction, but increases the torque in the same direction. Expensive to control. Separately excited is expensive to control because you have electronic control on your field, and you have electronic control on your armature. This is where they were in the electronic controls, and it was using a high impedance circuit called a mag amp to run the field. And the guy got in there, and he was trying to measure the field with his voltmeter. People think that a voltmeter has it's got infinite resistance. It don't. So Dennis got in there and put his meter across that high impedance sensor that sensed the field, and shut the line down. And luckily it was in the control houses, and it had where you actually did your troubleshooting. They had all the relays out, and all the electronics was in a little room. And Dennis was in the room, and we call it blue hats. That's all the boasters out there wore blue hats. They come running in, and Dennis didn't move. He stayed in this little cubbyhole back there. They didn't even know he was there. And they reset the line, it come back up, and Dennis snuck out, so they never knew he shut the line down. Number 4, galvanizing line, if anybody works at US Steel. A permanent magnet motor. This is what all our motors are on all our lines, used on both Amatrol and Festo manufacturing lines. Speed changes with armature voltage. We look at it with a voltage point of view, right? You understand? But when voltage goes up, current goes up, and speed goes up. Reverses by reversing the armature connection. Good speed characteristic, good torque, very low horsepower applications. So this will be, and we don't usually draw the symbol of the permanent magnets, we just draw the armature. Okay. Series motor, great starting torque, poor speed regulation. So the field is in series with the armature. So if the armature tries to slow down, it's going to drop, the current's going to go up, which causes the series field to go up, which causes the torque of the motor to go up. This is one motor that we can run on AC and DC, so some people call it a universal motor. using applications that require extremely high starting and run torque. Uh, Anybody know compressors? Some compressors, everybody knows this. So this is your starter on your car. It's used a lot in hand drills, uh, and you can tell it. So you got your hand drill up there running right, and you stick it into a low. What does it do? Slows down, but what happens to the torque? It goes up. Yeah, you get some of these, 20 volt motors, or even your old plug-in motors, and yep, it'll jerk that sucker right out of your hand if it gets caught. Anybody ever lost a drill with something? Very high starting torque, very poor speed. So this is the starter on your motor on your car. Used in a lot of compressors, used in some vacuum cleaners, and we've got a compressor motor around here somewhere. Compound motors, these are used a lot in industry because we can control both. We have what they call a cumulative compound and a differential compound. We don't really need to know, this is the symbol for them. They're separately excited. Cumulative compound, the shunt field, which is the parallel field, right? Aids the shunt field, high starting torque, but less speed regulation. Differential has good starting torque, but very good speed regulation. Typically operates at a constant speed. So sometimes these are called constant speed motors. So this is a combination of a shunt motor and a separately excited, and it's got a series field. Okay? DC motor speed control. Voltage increases, speed increases, voltage decreases, speed decreases. Normally used because if the speed control circuit fails, the motor will stop. Field, voltage increases, speed decreases, and torque increases. Voltage decreases, speed increases, and torque decreases. Not normally used because if the speed control circuit fails on a shunt, separately excited, or compound motor, the motor will overspeed. So whether you understand it or not, it works on something called counter EMF, and you'll get into that if you take motor controls on what this thing actually does. Normal way to reverse these things is to reverse the armature. That's industry standard. Because on some of these, you want to do it the same way every time, right? You understand that? And that way you don't have to guess. The problem we have is that if you lose the field circuit on a shunt or separately excited or a compound motor, them suckers can run away and they will sling themselves apart. We had some 200 horsepower DC motors on the number 4 galvanized line out at US Steel. And that's 200 horsepower, guys. And we had one, it had an overspeed centrifugal switch on it. It had overspeed connectors, but it slung itself apart 2 times, and we never figured out how it did it. Because that's the ones where they were controlled in both it was the takeoff reels and the take up reels. So you had not only had to control the speed, you had to keep the same torque on the thing, right? So these guys was running control on both of them, and that motor slung itself apart 2 times. Now, when I worked out there, I only worked out there about 5 years, I guess. So how do we control the speed of a DC motor? We can do, and I can't get my Arduino. My Arduino program's not on this, guys. I don't know. I think it might be on that computer. We can control it with a rheostat, but we had some cranes out there. They were 5-speed cranes, and that's all they did. They just had relays out there, and they would switch resistors in and out of the armature. And they were inside cages, and they got hot. They had fins on them. It's very inefficient to control the DC motor that way, but the electronics is really, the circuits are really easy. So I just had relays that would either short the resistor out or put them in there, and they were 5-speed cranes. We can use resistors. We could use a rheostat, or that's POTS being used as a rheostat. But you got to understand is that your motor's out here running. This guy right here's got an R, I square R, so these are not going to be used to run very, 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 uh, very high horsepower motors. So we came up with a method using what we call silicon control rectifiers. And what we would do is we'd start out on AC, and then we would end up with something like this. And then the motor would average that out. And what we would do with these SCRs is we would delay. We called it firing and so we'd end up with something like that. Now you wouldn't see it because across a DC motor, when you cut it off, the DC motor acts like a generator. So if you looked at this with an oscilloscope, it almost looked like DC. But what would happen is the average DC would go down and the motor would slow down. This was done for years. This was the drives that we had when we got US Steel SCR drives, three phase SCR drives. So that it was really really cool. And so SCRs. This is the way we do it now. This is called pulse width modulation. So what we do is we just put a string of DC pulses out to the motor. And if you look, the time per cycle never changes. So if you look at this line right there and that line right there, it never moves. And what your DC motor does is it averages it out. So the narrative, the DC motor sees an lower average voltage and it slows down. And of course, the further it moves out to DC, the faster the motor runs. This is called pulse width modulation. This is the way we do it now. In fact, this guy right here supports pulse width modulation. So this PLC supports this. So most of your PLC supports actually pulse width modulation, where we could send a code into the circuit and it would actually do whatever pulse width we wanted to do to control the speed. And I could do this, but I'll probably try to hook it up for next class. I'll probably run it off this function generator instead of my Arduino. I can't find the programs to run it. So the electronics is a lot easier. I mean, like I said, these are either on or off, and we can do it digitally. And program logic controllers love digital. So, like I said, all the PLCs I know of now have this feature. Reversing the electrical connection of the armature and not the field or the stator. This is the normal way to reverse a DC motor because if reversing circuit fails, the motor will stop. We could reverse the connection on the field, but on some motors, if that circuit breaks, it will run away. So instead of doing it one way for one motor, and then of course on a permanent magnet motor, the only option you got is to reverse the fields. We had a shaded pole motor. The clocks we had over in Japan when I was over there ran off of what we call a shaded pole motor. And to reverse it, you had to take the pole pieces off and turn it around. And we did that, and our clock would run backwards. People would come in and they go, the second hand was going this way instead of that way. So yeah, true story. Reverse. So we normally, I'm not saying you're not going to find this, but we normally don't do this because if you got a shunt motor or a separately excited motor or a compound motor and you lose the field, it seems like it's crazy, but it will because it works on something called counter EMF and the motor could take off. If you reverse both the field and the armature, the motor will run in the same direction. It will not reverse. So you got to change the relationship between the fields. So this is electronically. So we could do it this way. I don't know if you can see the different symbols, but the arrow's pointing in, the arrow pointing out. And what we would do is we change the polarity. If I turn on this guy and then I turn on this guy, then the motor would run one direction, and then the other two we would have turned off. So these are transistors, and we can make them act like solid state switches. This is what we're using in our sensors, syncing and sourcing sensors. PNP, positive, NPN, negative, right? So NPN syncs, PNP does what? Source. And you can actually see it here. So here's the plus, here's the minus. The PNP is connected to the plus, and the NPN is connected to the minus. And what would we do to reverse it? I would turn off those two, and I'd turn on the other two electronically. So now we would bring, of course, I'm drawing from positive to negative, but you can see what I'm doing. I mean, I can go the other way if you want to. Then we get this one, and then now we're going through this guy, and then we'll go up through that one. This is called an age control. We could do this with a program controller. Well, that's not true. It would be hard to do with a relay output. So this is one way electronically we could reverse a DC motor. Now, is this what, these are using FETs, but they work exactly the same way. You can see the arrows pointing out here, and the arrows pointing in right here. So one of them's called an N channel, and one of them's called a P channel. But we turn them on what? Opposite of each other. What you mean? Why? Well, we would turn all of them off. What's nice about this is we have a thing with motors, and we're fixing to look at that in a minute, James. It's called plugging. Plugging is when you reverse the direction of a motor without it coming to a complete stop. And we talked about this. So motors pull a lot of current to get them started. We call it starting current. Rule of thumb, if you don't have the chart, so if you look at most motors now, it's called code. That's all it's code, and it's got a code out there, and you can look it up on the chart, and it would tell you the multiplier to use the multiplier you'd use to figure out what we call our starting current. Well, the problem is if you reverse this thing and you don't let it come to a stop, it's going to pull that full load current until it changes directions. So it's pulling the full load current a lot, and it could kick your overload. I've seen it do that. So what's nice about this guy is we could literally turn all of them off until the motor came to a stop, and then we could come up here and y'all do it. If you got a ceiling fan, how many got a ceiling fan now? You got a little switch on the side. You flip it. What does that motor do while it's running? It's humming. You like it's just trying to do what? It's pulling that starting current until it changes directions. So to get a long life out of your ceiling fan, you should turn it off, let it come to a stop, right? Then reverse it. These are using relay contacts. This is what all ours use. Plugging, reversing a motor without stopping. Pros, it's a very simple circuit, can be done with double pole, double throw relays. Cons, draw starting current until the motor changes direction. Will reduce the lifespan of the motor. Stopping the motor requires removing power. So we could do this, but we'd have to put some type of control down here, which is what we do. So this would be what we call an H control. Can y'all see how I got that name? Because when we draw it, a lot of times it looks like an H. I come up here and close this contact, and then I come up through here. Then the motor would run in one direction. And I come back here and erase it. So this is one big advantage fluid power motors have over electric motors. They don't have starting current. You can reverse those suckers a heartbeat like that. Don't hurt them at all. Don't hurt them at all. I mean, you're just doing it with pressure. So that's one big advantage hydraulic or pneumatics motors has over these. On these electric motors, if you reverse them without letting them stop, it's going to pull that motor. And what's it called? What? Plugging. What's jogging? Yeah, this is when you run the motor in burst. If you took robotics, that's what we call it, jogging. So I got two options here on this one. We could still plug the motor, right? Or we could do what? We could put a timer in there, like James said, or we could. I've got a circuit over there on motor controls using a PLC. We don't teach PLCs over there. Eventually, hopefully, we will. We're trying to get the motor controls lab over here, by the way. And, so we got a PLC running a three-phase motor, and we're just reversing it. And that's what we do. We'll turn it off and let it time, and then we'll start it over. This is the guy that we were talking about. This is called stepper motor. So normally, if we look at the motors on this on the Amatro line, they use the H control. They use the H control over there, but they sometimes they plug the motor, sometimes they don't. What they have on the Amatro is they have the slip clutch on there. So when they reverse it, it slips and it's not actually running the load for a while, right? You understand, but it's still not good. Stepping motors, advantage, easy to electronic and control, disadvantage, low torque. A digital control motor that operates in precise steps. A step size is usually specified in degrees per step or steps per revolution. Of course, if they gave you steps per revolution, you could calculate the what? The steps per degree, right? Okay. You just take, if it's got a 100-step motor, which is what this is right here, it's a 100-step stepping motor, 360 degrees, right? 100 degrees divided by 360 degrees would give you the degrees per step. Or that's backwards. 360 degrees divided by 100. Bipolar stepping motors, and basically what we have on here is so stepping motors have a permanent magnet rotor. And then what we do is we electronically move the field. Oh, by the way, this is called half stepping. So if you have the electronics and know how, so notice it's actually energizing two fields at the same time. So this has it has 8 steps instead of 4 steps. So you can buy these double step controllers. We don't have any around here, so my program just single steps. So where do we have stepping motors at? Which line do we have a stepping motor on? Yeah, where's it at? On the index table, right? On the table. Yeah. And you can actually hear it hum. So most stepping motors you can hear hum when they move, if they move real fast. But they actually literally come to stop. They come at a stop on each step. It's just that if you do your steps fast enough, it appears to be moving in a single motion. We can run these suckers open loop. All we got to do is find a home position, and then once we find a home position, then we can control the position of the motor with steps. And I showed y'all how that thing finds its home position, right? It uses that inductive sensor, so it finds its home position. So we can literally stop that thing anywhere. Normally we show that where I get it moving, I flip the power off, and we turn it back on. It'll start single stepping until it finds until that inductive sensor clears. Then it steps back so many steps, and then it's lined up. So if you wanted to screw that up, just move that inductive sensor, right? And that happens a lot, guys. People, these mounts and stuff, they'll do what? They'll hit them or something and bend them, and then it don't work anymore. I'm gonna tell you how many times I saw that. This is the newer motors. These are called brushless motors. I need to find my. I need to find. We got one of these. So what they do on a brushless motor is that it has no brushes on it. It's a DC motor. It has no brushes. The problem we have with brushes, if you ever use the hand drill, and it's got the slot back on the back so the thing can breathe, and you're sitting there using it, what do you see where the brushes are hitting that commutator? What do you see all the time in a hand drill? Anybody ever use a hand drill? Sparks. Yeah. So these motors, you got to be really careful with using them in environments that got some type of gas or something out there. Also, the problem we have, and this is why we had to go to resistive spark plug wires, guys, is that the first signals that they were able to transfer through the air was just generating sparks like lightning. Uh, and we call them spark gap generators. So that's the way they were did. So the problem we have when these things arcs, they put out tons of electromagnetic interference, EMIs. And electronics and electromagnetic interference does not go away with each other. So all the fans in a computer are these guys right here, because they're inside the computer. They're cooling the microprocessor fan, the outside fans. So the big advantage we have with a brushless DC motor is that they don't generate electromagnetic interference. Now, what advantage you get buying a hand drill with a brushless DC motor, I don't know. But it's got to be electronically controlled, so this is why they're more expensive, because they got to electronically cause this field to do what? They got to electronically cause the field to move. So they're constantly causing this, and then the rotor is actually a magnet, and it just latches onto that. Smaller to stepping motors, but similar to stepping motors, excuse me. But the rotor does not step. Rotor is in a circular magnet around the outside. So here the rotor is actually around the what? The outside, yeah. The stator's electronically controlled magnetic field in the center of the motor. Very low MI used primarily in computers. But this is the big thing. If you look at some of your hand drills and some of your equipment, that's what they're advertising, brushless DC motors. What do you mean? These are just the different. Uh, oh, this right here. This is the graph that's indicating how the actual fields are shifted around the outside. So see, they're calling this C. So right now C is, and then I was trying to see the other one. Here's B. So it goes B, C, probably A, B, C, A, B, C, A, B, C. I don't see the A anymore. But what they're doing is they're rotating this around, north, south. And then what they're doing is they're actually showing you, I can see the B. So B and C, see what I mean? Yeah. So that's actually how they're switching the fields. So here current flow would be in one direction, and then they actually reverse the current flow to make it move, right? Yeah. So that's a good. I understand that now. So for some reason it's not showing up over here, but every once in a while you see BC, and it shows BC, and then it should move. And one of them, and then they're switching the fields like this. So you see sometimes the arrows point this way for a north, and then sometimes the arrows point the other way for a south. So you can see this is going to be. So what they're trying to do is, so if this is a north and this is a south, and the thing rotates, and sooner or later you're going to have to do what? You're going to have to swap them around. So that's a good question. I never noticed that, but well, I saw this, but I thought you was talking about these in here. But you see, the only thing they show is B and C every once in a while. So undoubtedly, the animation showed it moving around. So the advantage of it, and I'll see if I can find that after our next break. And it looks like we're not going to have any time to do a lab, so we'll probably yeah. What's the BC I was talking about? Oh, okay, it's red. Yeah, I don't know why they decided they used it's the I don't know why they did that because the color they used is the color of the copper, so they should have used another color. So this is not my animation, by the way. I got this off the internet somewhere. So yeah, you're right. And they don't show it moving up here, but you can see it. It shifts north south, and it causes this magnet on the outside, say the north. And this is a really good animation, and it shows you it's actually being pulled around while it moves, which is pretty neat. But the advantage of these, I know why we use them in computers because they have very, very, very low electromagnetic interference. So if you got a desktop computer, or the disk drives, if you got a hard disk drive, you don't have solid state disk drive. This is the motors that they spin the hard disk drive with. This is the motor when we had floppy disks. This is the motor they spent the floppy disk with. If y'all remember, in fact, we got an 8-inch floppy disk around here somewhere. I'm gonna see if I can find it, and we can pull the magnet off and actually see the coils around there. And it uses a Hall effect on the side to pick up the magnet to determine the speed. Yeah, these are permanent magnets right here. So notice this end right here never changes. You can see when it updates, and the south never changes. So what we're doing is we're causing this guy right here. So this is the armature. I mean, yeah, this is the field. We're causing it to do what? Yeah, so this and the stepping motor. We cause the field to rotate. All your other motors, we cause the armature to switch the field, right? With that. So the advantage of a brushless DC motor is that it has almost no electromagnetic DC motor. A servo motor is a motor that provides feedback. So not only do you run it at a speed, it tells you how fast it's running. So it's got some of the unit in there, and that's servo, by the way. Servo means feedback. So we call it a closed loop system. We call it a servo system. If you ever hear servo system, it means we tell it to do it, and then it does what? Tells it. So your cruise control on your car is a servo system. So that's what that term means. Good point. So that's a servo motor. So that's a servo motor is a motor that provides what? Feedback. And then we bring that into our system somehow and determine the speed. Okay, how much y'all know about AC motors? I showed y'all the induction. Didn't I show y'all the two coils that when I brought it together, the LED came on? Did I show y'all that? Okay. So what's required to induce an EMF magnetically? What's required? You're giving me the amount. Got to have a magnetic field. Got to have a what? A conductor. And what else? Got to have motion between the two. So if I can do this and motors work off the repulsion and attraction of magnetic fields, then what we can do is we can induce a voltage into the rotor, right? You understand that? That would generate a magnetic field. So we call these induction motors. So that means we put a magnetic field on the outside in the stator, and then the voltage and the current in the armature or the rotor is induced. Single phase, we have capacitive start, capacitive run, split phase, and shaded pole. Three phase, we have Y, delta, delta Y, round rotor, and synchronous. And of course, synchronous, we have single phase and three phase. Y'all understand it? It's single phase, three phase. Anybody got any problem with that? So what do we mean by three? So single phase, we run, and it's AC, we do this. And then we have one that we call the hot wire, right? And then we have a common. Okay. Three phase, what we do is we generate it on three different wires, and the three voltages are 120 electrical degrees apart. So this is about, and so one cycle, we call this a cycle, is generated on a circle. So one repetition we call a cycle, and one repetition is 360 electrical degrees. So this right here would occur at 90 degrees, electrical degrees. It crosses at 180. Then it crosses again at, this would be 270 degrees. And then this right here would be 360. And it's just like 12 midnight. What's 12 midnight? Well, 12 midnight is the end of one day, but it's the what? Start of the next. So what would happen is you'd have another alternation. So 360 degrees for this alternation on the left would be 0 degrees for the next one. That makes sense? So 120 degrees would be right in here. So what would happen on the other wire, we would have another guy that would start right here. And then on the second wire, I'm running out of loop. And then on the next wire, it would start right here. Now, so how much more power could we transmit? So we got to use two wires anyway. How much power would we be able to transmit if I add that third wire? Are we? .7% more power by adding one more wire. They're out of phase. So we could get, so the formula, what's the formula for power? Power is equal to V times I. Now, when we measure V and I, we usually only measure in one, and then this is times the square root of 3. So this is your power formula for three phase. And of course, the square root of 3 is 0.707, so that's 70.7%. So we can add, just by adding a single, one more conductor. We got to have how many anyway? 2. Okay. By adding one more conductor and using the difference between those, we don't have to run a ground. We can, or common on three phase delta. We don't have to run what we call a common. I can send 70.07% more power with one group of one wire. So if I'm going to send power over a long distance, or if I'm going to use a lot of power, then three phase is the way to go. If I'm going to not use a lot of power, it costs more to run all that copper, and you'd have to have 3 transformers all over the place. So if I'm not going to use a lot of power, then we use single phase. So your house has what? Single phase. Most of your big industries and all your big restaurants and stuff run what? Three phase. So that's the big advantage. But it's more expensive to run it just for your house, right? You understand? So if we ran that one more wire, instead of having one transformer up on the pole, we'd have to have what? 3. Transformers cost a lot of money. So high power demands, we use three phase. So three-phase motors automatically generate a rotating field. So you can see this. When A starts dropping down, B comes up, and it just constantly does that. So single-phase motors, three-phase motors are a lot more efficient than single-phase motors, but they cost a lot more money. So if you need a lot of high torque and really good efficiency, then three-phase motors go. Single-phase motors, these are very, very cheap. But we have to create a shift in the phase to cause them to do what? To rotate. So we have devices. If you take AC, you'll learn about capacitors and inductors. One thing that these devices do is they create phase shifts. So we have what we call a capacitive start motor, and we have a start winding. It's got a capacitor in it, and we put it in the circuit. We start the motor. Once the motor is rotating, it creates its own phase shift. So what we'll do is we'll kick it out. It's got a centrifugal switch on it, and we'll kick it out as soon as it starts coming up to speed. But the run torque is not as, for size of the motor, it's not as good as we could get more torque for a smaller motor if we left the capacitor in there all the time. So we have what we call a capacitive run motor. We have two capacitors on there. One of them we put a lot of capacitance to get it started, and then we leave another capacitor to get more torque for size. These motors cost a lot more, but they're a lot They're a lot smaller for the same amount of horsepower. Inductive motors, these guys, they are predominantly what's in your house. If you go out to your HVAC system, you'll see there's two brown wires running off, and you follow those off, they're going to go to a capacitor. They don't put the capacitor internal on those motors because those things are out in the air. And so if you got an AC motor that just hums at you when you put power on it, it's a high probability that you've lost the component that causes the phase shift. So you can buy a new motor for $200 or $300, or you can buy a start capacitor for about $20. But it's going to hum at you, right? If you can take the motor, you don't want to do this. You don't want to do this on something that's going to hurt you. But a single phase motor, if it hums at you and you spin it and it goes in whatever direction you spin it, it's a start capacitor, I guarantee you. Because what you're doing is you're stimulating the what? Yeah, the start capacitor. So if you can spin the motor and it'll come up, it'll start running in the direction that you did. That's the problem with it. The way we reverse a single phase motor, if it's reversible, is we reverse the connection on the start winding. That's the industry standard. You don't want to reverse the start winding and the run winding. If you do that, it'll run in the same direction. So you have to do that. So a lot of your AC motors, single phase motors like you've got in your house, you cannot reverse it. They either run clockwise or counterclockwise. My evaporator fan on my old Fetters air conditioner went out, and it was going to cost me a lot of money. So I went up to the air conditioner shop, and they had one that they pulled out. I went home and put it on there, and it ran in the wrong direction. So instead of pulling through the evaporator and blowing it up at the top, it ran like that way, good gracious, for 10 years. So, but a guy come out there and was putting Freon in it for me, and he said, "You know that motor's running the wrong way?" I said, "Yeah." "You know that's not good for it." I said, "It's been doing that for 5 years." So anyway, true story. Shaded pole motors. This is what we have in some of our pencil sharpeners. This is the one that we actually had to reverse the field. So a shaded pole motor, can y'all see this? So what it does, it puts a little inductor in here, and when the power goes up, it produces the phase shift here. So to reverse those, What you'd have to do is you take the actual field off, you pull it off and reverse it and stick it back in there. So those are basically non-reversible. This is the motor we had on our clock in Japan that we reversed. And we put the numbers back. Well, we painted the numbers on there backwards too. You know, so, and we painted it yellow. So this would be a start capacitor. So like I said, it's either going to be mounted on the motor, or there's going to be the industry standard two brown wires that run off, and the start capacitors mounted outside. These you got a little screw on the side. You can pop off the cover and get to your start capacitor here. So this would be a start capacitor motor. This is the symbol for the centrifugal switch. So what it does, it kicks it out right off the bat. I mean, you can hear it click. This is a capacitive run motor. Some people call it capacitive start, capacitive run. It's going to have two capacitors on it. One, it uses both of them to get it started, and then it leaves the other one in all the time. What's the advantage of these? That it gets better run torque for size. So normally you'll only see these. You won't see any of these in your house. You might see them out in industry every once in a while because they cost a lot more money for the same amount of horsepower. This is a split phase motor. This is probably what's running your washing machine, your dishwasher. If you got an electric dishwasher, it's probably running your dryer. These things don't have a really good low horsepower, but if you gear them right, they're probably the cheapest. This creates a phase shift with an inductor, and these are called split phase motors. How do you change direction? Change the connection on the start winding or the run winding. I'm asking. Do we change the connection on the run winding or the start winding? Start winding. Good. This is shaded pole motor. We looked at that. Three-phase motors. Three-phase motors generate a rotating field, so they don't have to have a phase shift. Delta motors, Y motors makes absolutely no difference. It's up to the manufacturer. Why are those things either Delta Y? So Delta Y, we usually draw it like this, even though electrically, okay. And Delta, we usually draw this like this. Now, Delta motor, Y motor makes absolutely no difference. It's transparent to you. All you know is it's got this voltage, this run current, and this horsepower. That's all you know. Delta Y motors, we can start at Y, and then which makes it draw less current and produces less torque, and then we can switch at Delta. That's the only thing. When you get into motor controls, you're going to be dealing with what we call a dual voltage motor. Dual voltage motors, what that means is we can wire it two different voltages. Most industry has more than one voltage. So, which one would you prefer? If you have if you can wire a motor for low voltage, so our motors we can wire them for 240 or 220, and we can wire them for 440. So, what would be the difference? Which one would be more beneficial? Why would it be cheaper? Yeah, but it's a horsepower motor. We don't pay a current bill, and we don't pay a voltage bill. We pay a power bill. So a motor's rated at a voltage, but it might be a 5 horsepower motor. So that means if you wire it 120, it's going to run 5 horsepower. If you run it 240, it's going to do 5 horsepower if it's generated. It's about 746 watts per horsepower, but when we wire it high voltage or we wire it low voltage, it's going to cost us exactly the same amount of money to run it because we're paying for horsepower. We're not paying for 120 volts. We're not paying for 240 volts or 440 volts, right? You understand that? So 440 would, if it's available, that would be the way I wire it. Why? We have to wire the motor. We have to wire the motor to run on 440. So if you wire it to run on 220 and you hook it up to 440, you're going to burn the motor up. If you wire it for 440 and run it on 120, you'll probably burn the motor up too because it won't create a start. What advantage does high voltage have over low voltage? Less current to produce that, which means I can run smaller wires out to the device. I can understand, but it costs you the same. Your high wattage devices at your house, what does it run? Your high wattage devices, what does it run at your house? 220? Wow, what advantage does it have? The electrician could use smaller wires. So instead of running through your ceiling and under your house, right, you understand, instead of running, 4-gauge wire to run your outside compressor, they can run, 10-gauge wire, right, you understand. So that's the only, what advantage does low voltage have? Where are all your 240 plugs at? Where's the 240 stuff at? Where are the plugs at? Down its floor, right? Or hardwired. Where are all your 120 plugs at? What advantage does the 120 have over 240? It's safer for you. It's safer for you. So the advantage of low voltage is it's what? Safer. The advantage of high voltage is what? We can send a lot of power over what? Smaller wire. So all your 120 volts plugs is dangerous as what? 240. So a lot of companies have multiple voltages. Instead of carrying a 440 volt motor and a 220 or 240 volt motor, they just have a motor that they can. Yeah, we can wire it. When you wire it, if you wire it for low voltage, don't run it what? On high voltage, either way will burn it up. So this shows you 3-phase and how it rotates. So you can actually see the power doing what? Moving, right? See the power right here? So what the advantage of 3-phase is it automatically creates a rotating field for your armature. How do you reverse them? Anybody know? What's that? Yeah, industry standard is to switch 1 and 3. You can switch any 2 phases, and it changes direction. But industry standard is to switch 1 and 3. Why do you want to do industry standards? If somebody else comes in there and works after you, right? They know what to expect. So reversing the motor. What's the normal way to reverse a DC motor? Switch the connection on the armature, right? What's the normal way of reversing a single-phase motor? Switch the connection on the start winding. Good. What's the normal way industry standard way of switching a 3-phase motor? Yeah, 1 and 3. This is something that I put in. This is the last thing we're going to look at, guys. I know y'all ready to go. I know y'all hate all these lectures. I understand that. But the speed of an, and this is why we had so much problems controlling the speed of an AC motor, is that the speed of an AC motor is set by RPM, and this is the outside frequency. This is not the rotor. The rotor will always run slightly slower, so it could have a change in magnetic field to induce the voltage, and we call it slip. So the speed of an AC motor is 120 times the watt frequency divided by the number of magnetic poles minus the slip. So how could I control the frequency of an AC motor? Looks like I've got two ways. We can change the frequency, but we can't, but that's a good point. Or we could change the number of poles. So that's what you're doing. If you got a ceiling fan and you flip that switch, what are you changing? You know, change the frequency, you're changing the what? Number of poles. Right? Why can't I just change the frequency on the AC motor? Anybody had AC? We miscall them variable frequency drives. If I just change the frequency, we'd burn that motor up, or the problem we have is that the motor is an inductor. And so if you have AC, the amount of inductance that motor has is 2 pi FL. So that's frequency. So if I raise the frequency up, the opposition goes up. So the motor would stall. If I lower the frequency, then the motor would burn up. So we call them variable frequency drives, but you have to adjust the voltage along with the motor. So we call it, when you program a variable frequency drive, you tell it the voltage is supposed to run at, and you tell it the frequency it's supposed to run at. Then it calculates it to what they call a volt per hertz. So if you raise the frequency and the voltage at exactly the same percentage, you can control the speed of the motor. So as the frequency goes down, the voltage to the motor goes down, as the frequency goes up. So that's why, once they figured out how to do that, then now AC motors are predominant speed control. And why? The motors are so much cheaper. Yeah, that's a good point. And that's what that explains. So this shows you pulse width modulation. So we use pulse width modulation to change the frequency. It's really cool. And a lot of electronics, but we can now do that and control the speed of a motor. So we call them variable frequency drives. I like to call them variable speed drives because most people think you're just changing the watt. Can't do that. So this shows you pulse width modulation. So they change what we call the duty cycle, and the motor actually sees a different watt. Sees a different voltage. All right, guys.